recording. Yeah, I think the problem is it doesn't show up. 1 second. Yeah, it doesn't. Okay, it does show up in the same place. Okay, good. Okay, so we'll get started. All of you can see the PowerPoint, right? The material that I'm sharing, right?
Yes, sir.
Okay, great. So a quick recap. So yesterday what we saw or what we discussed was there is this certain kind of naturally occurring material by the name of quartz. And yeah, I mean, essentially quartz is also associated with astrology, non very scientific domain. But yeah, so quartz is a naturally occurring crystal. Its composition is like silicon dioxide. It's made of silicon dioxide molecules. And yesterday we saw that okay, if a certain force is applied to quartz crystal in a certain direction, then it behaves in a certain way. So 1 second, yeah. So it behaves in a certain way. We saw that if we apply a force, then the yellow cations, the silicon ions, the positively charged ions, and the negatively charged anions, the oxygen ions, on application of a force in a certain direction, the center of charge for the positively charged ions and the negatively charged ions, there is a asymmetry that creeps in, and because of the asymmetry, so here we can, for example, here this is the positively charged center, and this is the negatively charged center. So because of this, a dipole on the application of a force, a dipole kind of appears, right? And because of this, I mean, essentially this happens because the center symmetry of charge is lost on the application of a force. And because of this, the material exhibits a property by the name of piezoelectricity. So one intuitive question. So when we apply the force, so what happens to the total charge in a piece of crystal? So let's say we have a piece of crystal which we are going to use as an application. I mean, as a transducer, let's say. And I'm right now using the word transducer very loosely. We'll talk about it in a little bit more, engineering or scientific sense. But let's say we have a transducer with a quartz crystal, and if we apply a force on the quartz crystal, what happens to the total charge? I mean, we have discussed this is how the crystal looks like. This is the optical axis, x-axis, which is the electrical axis, and the mechanical axis, y-axis. But on the application of the force, can someone tell me, like, what is the net charge in the crystal? If we take a crystal, we apply a force. What is the net charge? Can we say that there is a overall net positive charge or overall net negative charge in the crystal?
Like the net charge will be 0, right?
Yes, correct. The net charge will be 0 because we have not done. There's no electrical source associated with the crystal. We are just saying that we have chosen a crystal and we are applying a force, and we are saying that the net charge will be 0, right? So keep that in. Let's keep that in mind. And with that, we said that we'll define 6 axes. The x-axis as axis 1, the y-axis as axis 2, and the optical axis as the z-axis, which is the third axis. And then the angular axis around which the shear force will be talked about. I mean, the shear force is on the axis 4, 5, and 6. And we also said that the total charge is related to the force with a proportionality constant, and we are calling it a piezoelectric coefficient D. And there are many other piezoelectric coefficients which we are going to look into them subsequently. And we said that on the longitudinal effect, the way when we apply the force on the x-axis, the crystal shows a longitudinal effect, and which means that the total charge developed on the positive plate and the negative plate of the crystal is independent of the physical dimensions of the material, and that also you can think about if you go back to this diagram, right, and look at it carefully. So as I said, I've tried to map this diagram from here to here. I mean the atoms, the silicon and the oxygen atoms, I've tried to map and then create a 3D structure. So you can think, why the x-axis and the y-axis, why they behave a little bit differently. But as electrical engineers, while we will try to understand the crystal structure, but our goal is more on understanding, the sensor. See, one of the challenges of this course is, I come from a pure, electronics background. But one of the challenges of this course is, this course has some amount of material science involved, some amount of mechanics involved, and then of course the electronics portion, which is the instrumentation portion. Essentially we call it instrumentation, but these are all electronics, right? So one of the challenges of this course is to strike a right balance between these three domains without losing focus or without forgetting that we are all electrical engineers. So it's very important while we understand the physics or the material side of it, and also try to understand the mechanical behavior of the sensors or the transducers. But our main goal is to develop the electronics around it, which is what we are going to go into shortly. So you can think, try to think why the x-axis and the y-axis are so much different in terms of their behavior. So when we say Q equal to dF, and if we normalize both sides of the equation with the area of the plates, basically we divide both sides with area A on both sides. Then we come up with a quantity called P, the polarization factor, which is nothing but the charge density per unit area. And the force, we replace that with sigma, which is again a pretty well-known. Actually, later on in the slides, we'll replace sigma with some other letter of the alphabet. But for now, we are still sticking to our, whatever we have learned in first year mechanics. I hope they still teach you mechanics in first year. So the stress is given by force per unit area. And then we saw that, okay, because the polarization effect is essentially a vector. And when we talk of polarization, there are three axes associated with it. The electrical axis that are associated with are three. So we write the equation Pi as a summation of the overall impact of the total polarization developed because of the forces or the stress applied in the different axes. So the number of mechanical axes that are associated are 6, not 3, right? And hence we can write the overall polarization vector in matrix form as P1, P2, and P3, and we can relate them with the stress. So even though here, one thing to keep track of, this sigma 4, sigma 5, and sigma 6, I have kind of used the symbol sigma here, but essentially, if in certain textbooks you can find that they're calling it tau, which is nothing but the shear force, which is one and the same thing, just that to be consistent or to make my life easier with symbols, I've stuck to sigma. Right. So basically, if you see the polarization vector, which is across three axes, is related to the overall mechanical stress that we apply on 6 different axes, and this is the matrix which shows us the coefficient, which is essentially physical properties of the material. So for silicon, these values will be something, and for, let's say, polymers, this will be something else. For ceramics, it will be something else. And if you want to get a quantitative feel of what are the D values for different material, we can have a short session on that sometime later on. But for now, we'll try to understand the whole thing a little bit more physically and in very simple terms. And so what is Dij? So just to carefully look at this coefficient that we have defined, Dij is the polarization coefficient on the ith direction, very important, ith direction due to the mechanical force on the jth axis. So basically the subscript I denotes my or our electrical behavior because of a force or stress applied on the jth axis. So this is the mechanical, the subscript associated with the mechanical quantity, right? Any questions up to this point? I've tried to keep things very simple, and as we build on to the course, things will become more and more involved. But we'll start off and we'll try to keep things simple because as an engineer, that is our goal. I mean, if some of you go on to join the industry, you will see that as engineers, unlike what is the general perception, our engineers, the goal of the engineering community is to keep things simple and do things which are required. Meaning, so for example, if you're developing a product, you will see that this question will always keep coming to you. If you're trying to alter something, or if you're trying to do something additional to whatever is existing, we have to give a very good explanation to why we want to do that. And until and unless it is absolutely necessary, we as engineers, we don't touch whatever is the existing solution, right? So we'll try to keep things simple. So then we discussed that, okay, we showed that this is the transducer arrangement. We have a piece of quartz crystal, and being consistent again with the axis that we have already defined, the electrical axis is the x-axis, the optical axis has the z-axis, and y-axis is the mechanical. And we said that, look, if we have to kind of quantify the physical component, which is nothing but the force or the stress along the x-axis to an electrical signal, this is what we will be doing. We'll have a metallic electrode, and it's important to understand why the metallic electrode is needed. And because of the metallic electrode, we also have inherently, along with the transducer, we also have an inherently associated component, which is nothing but this capacitance Cx. Because we have two metallic electrodes, and in between the metallic electrodes, we have a non-conducting material which works as a dielectric. The material is, of course, silicon dioxide, because that's what we are discussing for now. So it's important to understand that we also have a capacitor between these two plates, right? And the capacitor value yesterday we discussed is given by the permittivity, the absolute permittivity of the material multiplied by the area of the plates, which is nothing but length and the breadth as shown, divided by the distance between the plates, which is nothing but the thickness of this material, T, right? And then we said, okay, so far so good, and we have a voltage which is given simplistically as Qx by Cx. Qx is the total charge that is developed on each of these plates on both sides, right? So this is Qx, and since it's a transducer, it is proportional to the force, and the proportionality constant is D11, and it makes sense it is D11 because we can see how the material has been aligned along the axis. So our x-axis is the the first axis, right? So the field, electric field in this case, is on the x-axis. So that's the reason why we are using the first Let me, yeah. The first subscript, oops, I think, yeah, I didn't do any better. So the first subscript is the electrical subscript, right? And the electric field is on the y-axis. So hence we are talking of D11 in this case. And that multiplied by the force that is on the x-axis gives the total charge Q. And Cx also, so what we have done is we have just replaced the value of Cx in this given equation. And with that equation, what we are saying, we are just manipulating the equation. So Ex is nothing but, as I think yesterday somebody also pointed out, that Ex is nothing but Vx by T. So this is what we do. We have just brought T on this side, and which means, if we were to relate the physical quantities, the mechanical physical quantity with the electrical quantity field by another new coefficient, G11. So G11 is related to D11 by this equation, right? This is what we discussed so far. Very simple, nothing much to remember. And by the way, also the way I will try to conduct the class is where you don't have to mug up things. Some equations probably will have to, kind of keep a tab on, but we'll try to keep the equations also simple, because later on we will see when we will be dealing with ultrasonic transducers and all, there will be wave equations and stuff like that that will come in. But my goal will be, to keep things to a point wherein, we don't get into too much of large equations which you have to mug up. And even if the equations which we have to remember, I'll try to make it in a way where you get a physical understanding or a physical intuition about the equation, and you should be able to write it without much problem, right? So if you see here, nothing much to remember, just that we have used those two different coefficients. One of them we are calling D, and D we are relating, D we have used to relate the charge and the force, whereas the coefficient G, we are relating it to the electrical field that has developed to the stress, right? So that's what we'll remember. And now we'll also, so we talked about quartz, and quartz is good. It's a physically, naturally occurring material. But we human beings, we always try to develop, we try to synthesize materials with, for of course, given obvious reason. One is, one can be the first reason why we synthesize materials, can be the scarcity of the first material, quartz itself. That can be one reason. Which is actually not the case in this in this scenario. We synthesize so that we get better properties to realize our end goal of realizing or designing or developing transducers. So there is certain kind of crystals by the name perovskites, and the general formula for perovskites are it's given by ABX3. So I'll take a pause here. So please see how the perovskites are kind of arranged in a, so this is the crystal lattice of a perovskite. So these are all ceramics actually. So these structures, the ABX3 structures, you can see how the atoms A, B, and X are kind of arranged. So first things are A is a positively charged cation with +2 positive charge, and B is again usually a metal ion like titanium or iron, and X2 is an anion like oxygen. It can be some other ions. We'll see if there are certain examples we have taken other than oxygen. But so typically, the take home. So whenever you see material of this general formula, ABX3, you will probably understand that this is a perovskite. And the reason why we are talking of a perovskite is, of course, in the context of a sensor or a transducer, right? So if you look at this structure, so this X, which is our anions, the oxygen ions, are located right at the center. So this is a cubic structure, and X, the oxygen ions in this case, are located right at the center of each of the faces, 6 faces of the cube, 1, 2, 3, 4, 5, 6, right? And we have 8 corners. So the positively charged cations, the large cations, which are nothing but A. So these guys are sitting in the corners of the cubic of the cube, and the second metal ion, which is B plus 4, the cation with plus 4 overall charge, is sitting right in the center, right? And an example of ABX3, a perovskite material, is barium titanate. Okay, so now we'll take a closer look at this structure. So if we take a closer look at this structure, right? Be careful, I have changed the location or the how I have denoted the same atoms in the second picture. So in the first picture, the A cations were sitting in the corners. It's the same structure, just that I've redrawn the figure to give you a better understanding of what is going on. So these A guys right now, so earlier in the first diagram, the A cations were sitting in the corner. Here, the A cations are sitting in the center. So these are, I've mentioned these are large cations. So in this diagram, I have shown A to be sitting right in the center, right? And what are the X, meaning our oxygen ions sitting? So the red guys are the oxygen ions sitting here, and where is our B cations? So the B cations, so you can see here, these are inside. So these are the B cations, right? Which you can see there is some faded kind of a ball inside this prism, right? So a few things to note. So the A site has the reason why the A needs to be a little bit big cation, because if you see, it has 12 covalent bonds, 1, 2, 3, 4. You can count and you can try to visualize how each of these A cations are bonded to the anions. So there are 12 bonds on the A site, and B site has 6 bonds, and that is straightforward to figure out. So here, this intermediate large guys, right, which is sitting inside the prism, has 1, 2, 3, 4. In one plane, it has 4, and then this is the 5th and the 6th, right? So there are 6 bonds, right? So what happens is, in this structure, so why are these perovskites important? Because just like in quads, right, what we tried to do was, on the application of a force, we want to realize a structure which will have a center symmetry in general, but on the application of the force, that symmetry will be disturbed, and that will create dipoles inside the material. And what is the dipole? Dipole is nothing but, if we have a charge pair, a negative and a positive charge pair, one dipole has a vector given by, so this is the dipole, let's say P, small p, and this is given by Q times D. So let's say this is a single charge Q, and this is the distance D between, so this D is not the D coefficient we are talking about. This D is the distance between these two charges, right? So the dipole that is developed will be given by P equal to QD, right? So, so the goal is to realize crystals or crystal structures which will, behave in a way that on the application of a force, the symmetry or the way the ions are kind of bonded to each other inside the material, on the application of a force, that symmetry will be disturbed and dipoles will be formed, and then there will be, even though the net effective charge inside the material remains zero, which is what I think one person pointed out, even though the net material charge remains zero, we will see an accumulation of charge on, there will be a net electric field that will develop, because some of the charges, the positive charges will move to one side and the negatively charged cations will move to another side, forming electrical dipoles, right? So we will try to realize or manufacture material which will have this behavior, right? So going back to again the same crystal structure that, so this is the same crystal structure. This I just kind of zoomed in to show how, ABX3, how each of them are kind of tied to each other or bonded to each other. And but now I'm going back to our original diagram, this diagram, and here I will be introducing 2 points or a couple of important points to note. Is a parameter, another physical parameter, temperature, right? So yeah, so we are talking of temperature here. So so each material has a characteristic temperature associated with it, which is known as, let's say, the Curie temperature. So what you can see here, if the temperature that is applied or the environment that the material is sitting in, if that temperature is more than the Curie temperature, then what happens is this guy is which guy? This guy, which was sitting right in the center, is B, right? So B is nothing but these transition metals like titanium or iron, right? So this guy is sitting right bang in the center of the cubic structure. It is right in the center. So what that means is, for a temperature which is more than the Curie temperature, the net dipole seen inside this cubic structure, because this guy is sitting right in the center, the net dipole, basically there will be no dipole formed above the Curie temperature, right? Now what happens below the Curie temperature? So typically Curie temperature, the goal, so when we are designing or manufacturing material, the goal is to, so okay, let me not tell this, let me ask you. So for a desirable sensor that we are designing for real world application, right? What should be the value of the Curie temperature, you guys think? Should it be, let's say, a low temperature like cold, like -20, or should it be the room temperature, 25, 30 degrees centigrade, or should it be high temperature? What should be the value of the Curie temperature? Any guesses? So when we are designing or we are manufacturing the material, what should be the goal of the engineer to make the Curie temperature? Should we try to keep it low? And the physical significance I've explained, that if the temperature, so we are talking of this in the context of piezoelectricity. So it's very important to remember that we are in instrumentation device class and we are talking about piezoelectricity. And we are talking about piezoelectric material. So in this context, we explain that above the Curie temperature, the dipoles that will be, showing up inside the material structure, that will kind of be non-existent. Whereas below the Curie temperature, we will get an effective dipole moment, which we discussed as the distance between the net positive charge center and the net negative charge center. So the dipole moment will be there if the material is in an environment less than Curie temperature. And in that context, my question to you is, when we are developing the material, what should be the goal? What kind of material would we try to develop? Should we try to make the Curie temperature high or low, or the room temperature? Any guesses?
Lower.
Okay, Nan Jyoti is telling we should try to make it low. Okay, anyone else who says no, it should be the room temperature? It should be low. Okay, why, Nan? Why do you think it should be low?
So because we don't want the polarization to happen before we apply the force, because we are talking in sense of the piezoelectricity.
Oh, okay. So see that this is where I fail, right? To explain. So good that, but I appreciate that you are trying to relate your answer to what we have explained. But anyone else with some other answer? Come on, guys, give a shot. I mean, no big deal, right? We are just discussing, and let's not take the subject too seriously. Okay, I mean, there's nothing, there's nothing there in the subject to be taken too seriously. We all want to score good marks, and we will get good marks. That's not a problem, but or good grades, right? But then I think let's try to understand whatever we can, right? Let's try to make good use of our time. And so come on, give me an answer. What do you think should be the Curie temperature? So anyone else wants to take a shot? Come on, guys, give me some answer. Not a big deal, right? And it's perfectly okay.
According to me,
Go ahead.
According to me, it should be low.
Okay, who
because
is this?
as
Who is this? Saurabh. Okay, Saurabh. Yeah, go ahead. Give you a reason.
So the same reason as what Nan Jyoti gave. So that's what I think.
Okay. Anyone else? Okay, so the answer is actually Curie temperature. We'll try to make it as high as possible, and it's my mistake that I couldn't explain. Or let me revisit this a little bit. But I understand why you are saying it should be low, because what both Saurabh and Nayan mentioned, that if we want the polarization to develop on the application of the force, is what has been the understanding based on the discussion that I've been having so far. So let me correct this. So typically what happens, right, or the way we design the transducers, that even without application of the force, there is an existing polarization that is already there, meaning there will be an existing dipole moment. Even without the application of the force, there will be an existing dipole moment in the material, right? Even without the application of the force. So what happens is, on the application of the force, the dipole, the dipole moments that are there inside the material, on the application of the force, that changes, and because of which the charge that is there, the net charge that is there on, let's say, the both plates of the transducer, the net charge changes. So essentially, the answer is, we try to make, and the reason why it should be also high, just think of it, right? If we make the Curie temperature low, let's say we try to make it minus 10 degrees centigrade, and we are trying and sitting here in Kharagpur, trying to use this, transducer, right? But the temperature is well above, let's say, 20-30 degrees centigrade, right? So what happens is, because the material is already sitting above the Curie temperature, right, there will be no dipole moment observed at all, right, on the application. So what happens is, above the Curie temperature, basically you can say the piezoelectric property itself is lost, meaning the characteristics of piezoelectricity, that itself is lost, because we can see, as in this case, right, this big guy here is right in the center, And on the application of the force, maybe it will probably still show some polarization, but that's what not we are interested in. We are interested in, so typically what is done is we try to make the Curie temperature as high as possible so that we can use the temperature. And the typical, whenever we are talking of products, and that is true in all electronic products, the typical usage range is from minus 40 degrees centigrade to 125 degrees centigrade, right? So this is the typical range of temperature for consumer products. For military, it is a little bit more, or for automotive also it is a little bit more. So for that we call it extended temperature range. That becomes from minus 50 to 150. But the electronics or the transducers that we design, typically we want to make them work from minus 40 to 125 degrees C. And if we have the Curie temperature somewhere in between this range, that's not a good thing to be, right? Because then the property of the transducer becomes some function of the temperature, which is not desirable at all, right? If we are designing a transducer to measure force, we want it to be dependent on only force and nothing else, right? We want it to be independent of temperature. So the goal is to realize material with higher and higher Curie temperature. So typically what happens is, this is what the second picture is actually saying. So typically what happens is when we are developing piezoelectric transducers, what we do is these perovskites are taken and it is heated close to the Curie temperature, or in some material or in some websites you will see they heat it actually above the Curie temperature, which can be let's say it's 600 or 700 degrees centigrade. Few places they say they heat it actually a little bit above the Curie temperature, and then while cooling, a strong electric field is applied, and that is known as the Poling direction. Poling, P-O-L-I-N-G. A strong electric field is applied to the material when the material is cooling from a temperature close to the Curie temperature. So when that strong electric field is being applied, what happens is, and when the material is cooling from the Curie temperature, so what happens is this particular guy here, the ions will move in a direction which is commensurate, or which is which will be in line with the externally applied electric field. And that becomes very important because, for example, here, this guy is a positively charged cation, right? That's what we discussed, right? So in which direction? So here in this picture, for example, we have shown that this cation has moved to the above this particular plane, right? So in which direction do you think the Poling electric field would have been applied? So that should be pretty straightforward answer, right? Because it's a cation and this guy has moved upwards. So the Poling field must have been applied in this direction, right? A strong electric field, E, external field E, must have been applied in this direction or in this direction. Sorry, I kind of messed up, but let me twist this into a question. So the Poling field should be applied in which direction? Poling field is the external electric field. So what should have been the direction of the Poling field if this guy has moved up in this direction? Take a shot, guys. Yes, Saurabh, you want to say something?
Sir, in downward direction?
Yes, because so what happens is, so Saurabh, why don't you explain why it is in the downward direction?
Sir, because we want to counter the movement of the dipole, we want to shift it towards in the middle, right? So that's why.
No, see, the thing is, what we have done is the goal is we have moved this cation So basically, okay, let me ask, forget all this piezoelectricity and all that. So let's say I have an electric field, right, in this direction, E. So the electric field lines go from positive to negative direction, right? And if I have a positive charge, Q, in which direction will the electric field go? I mean, in which direction will the positive charge move? Should it be
the negative?
So
yes,
right.
it will move to the right? So now if this positive guy has moved upwards and we have applied an electric field, external electric field, in which direction would we have applied the external electric field? Upwards, right? So not downwards, sort of. So we have applied the electric field upwards, which has gone, so which moves this guy up, because of which there is a dipole that we have created. Note what is the direction of the dipole. When we say that there is a dipole created, right? What do we say? The dipole direction is, let's say this is positive charge Q plus Q, and this is minus Q, right? Sorry, and what am I doing? 1 second. This is negative charge. So this is negative charge minus Q and this is positive charge plus Q. And when we say that there is a dipole moment, how do we draw the dipole moment? We draw the dipole moment from the negative charge to the positive charge, right? So in this case, the positive charge has moved up. So essentially we can say that the positive center, the center of the net positive charge is upwards and the negative is downwards. So the dipole moment is from downwards to upwards, right? Which is in the same direction in where we applied the external electric field, right? So the external electric field that was applied was in the upward direction, but the field that is generated now inside the material, that is in which direction? That is in opposite direction. And this is what I think probably Sora was referring to, that the internal electric field that has been generated by this process of pooling, that will be generated in a way to counter the external electric field, right? That is clear, right? I think that's what probably Sora was saying. He was talking of countering the external field. So it's important to know the polling direction. So whenever, later on in the slides, you will see I've taken examples of the transducer and I've used this arrow in different directions. So what that means is that is the naturally, basically even without the application of an external force or an application of an external field, there is a naturally occurring dipole moment that is there inside the material, and that is denoted by the arrow. So if you see here, right, the arrow is moving pointed from bottom to up, because as we said, this guy, the positively charged ions have moved up, and so effectively the center, the positively charged center, the positive center is upwards and the negative center is downwards. So this arrow shows the direction of the dipole moment inside the material. And this we will be, in subsequent slides, you will see when we also do, some examples, you will see this arrow being there. And the reason why we show the arrow in upwards direction, because it gives us, so basically, every time we are not going to draw this crystallographic, this crystal structure, right? We are just going to replace this by a capacitor, and, we are going to show, so let's say we have a transducer material, let's say piezoelectric material, and we have shown the arrow like this, right? So what it means is, if we say that the material is nothing but a capacitor and the arrow is existing like this, what it means is the positive charges are on the top plate and the negative charges are on the bottom plate, which means the dipole, the net dipole moment inside the material is pointing upwards, right? Which means the electric field, internal electric field, is pointing in the opposite direction of the pulling direction, which is downwards in this case. This is clear, right? Or have I managed to confuse you guys? This is clear, right? This is very important because all our exercises we are going to do will be based on this. This is clear, right, guys?
Yes.
Okay, great. So yeah, okay, Nayan, thank you for your response. So it's 12:50, so let's see what else. Okay, so this is what we said, that it can be induced through pooling of ferroelectric crystals, ceramics, or polymers. So there will be, by the way, I mean, I've seen people's career taking strange turns, right? I mean, I've seen electrical engineers go on to become, do the job of chemical engineers. And I have seen chemical engineers go on to become and do the job of electrical engineers. And trust me, that is true. I mean, you can ask me, how is that possible? It is possible because there are quite a few of you guys, right? Once you land up in the industry, there will be interesting career openings that you will have. And if you find interest, and if you think that taking this opening will be good for you, then you end up in a completely at least perceptually it will be completely different, right? So that is the reason why such subjects, while it is challenging to kind of understand because it has multiple domains involved, but we as faculty members, I will try to give you a flavor of little bit of the mechanics as well as the physics and a little bit of fabrication also, so that who knows where you guys are going to land a few years down the line, and maybe some of these things that you learn will be of help, right? So that's where this talk on crystals, ceramics, and polymers. Polymers have very interesting characteristics. For example, if you were to do your doctorate, I mean, if you were to go on to do your PhD on medical electronics, for sure you will be countering polymers there. And polymer has very interesting properties, and most important is polymers are biocompatible. So for example, you can many of these medical devices which we implant inside the human body, those are developed using polymers, right? We are not going to get into the details, but that's the reason why I've mentioned some of these words here. Again, nothing to kind of sweat or nothing to mug up, but just to be aware that piezoelectricity can be observed or can be developed in materials other than naturally occurring materials. We talked about quartz, we talked about perovskites, right? And we also talked about how the material is kind of pooled to kind of develop a net electric charge, not net electric charge, actually net electric field inside the material, right? One thing to note is even when we are applying high electric field externally, it's not that all just like in this class, right? We have a class of 40 students, right? And I'm sure not all of you are equally interested in this subject, right? For some of you might be taking some interest, some of you might be thinking of what is going on at home, or some of you might be already thinking, you'll have to, your next career step or whatever, right? Not everybody will be perfectly aligned with the course or what is being taught, right? So similarly, when an external electric field is being applied, we have to remember the mobility of each of those domains that are there, each of the crystal domains that are there inside the material. Not all of them will change the direction, but some of them will, or most of them will, and that will result in a net polarization, which will create a net electric field inside the material. And what happens is, after we remove the applied electric field, these domains, they don't go back to their original or initial orientation, right? Meaning my goal will be, after you attend the class for one full semester, there is at least something that you take away from this course, and don't go back to your state that you are there after the end of fifth semester, right? You must be adding something, right? So similarly, once the electric field is taken away, not all of those domains kind of revert back that will be there, right? And this is what we will call as the coding direction. So we'll stop here today because in the next few slides it may be a little bit boring for you, and then after that there will be a little lot of interest because there will be maths and electronics. So we'll stop here today and continue the class tomorrow. Any questions so far on this? And guys, please understand that I'm trying to, this subject itself is not the subject as such. I mean, this topic itself is kind of new to me, but I'm trying to kind of explain to you in the simplest possible ways. But please feel free. I will take some feedback from you guys maybe after a few weeks, and please feel free to give me your feedback so that I can improve on delivering the material. I'm trying to take pains to develop the material also. You will not find the course or the topics that I'm covering in one consolidated book, or it's not there because I'm taking the help of many different stuffs, and then I'm making my, I'm putting my own thoughts in arranging the subject, and the diagrams are also actually, most of the diagrams are drawn by me. Not all, but quite a few of them. So please feel free to kind of give your feedback. I will seek your feedback, but hopefully, you take away something from the lecture, right? So we'll stop here today. And in case you have any questions, do feel free to drop in a mail. But otherwise, we'll talk again tomorrow, right? Thank you.
Thank you, sir.
Thank you. Bye.